F-35B is often described as the most advanced fighter ever built, a true jack of all trades. It blends and improves upon the capabilities of the F-16, the V-8B Harrier, and even the B-2 stealth bomber. It is a highly maneuverable machine, able to strike both air and ground targets, while borrowing lessons in stealth from predecessors like the F-22 Raptor and F-117 Nighthawk. On board, the F-35B carries a suite of advanced sensors and computing systems that share information almost instantly with Allied aircraft without sacrificing stealth, displaying everything directly onto the pilot's helmet visor. This creates unparalleled situational awareness, enabling a formation of F-35s to fight with the coordination of a hive mind. Perhaps the most dramatic feature of all is its ability to transition from conventional flight to vertical flight at the push of a button, using directional thrust and a massive hidden vertical turbofan to land like a helicopter on the small amphibious assault ships used by the U.S. Marines. Packing so much into a single airframe is an extraordinary engineering challenge. Stealth design demands careful shaping of the aircraft's exterior, forcing unavoidable trade-offs. Contrary to popular belief, stealth isn't about making an aircraft invisible, it's about delaying detection as long as possible. For bombers, that means slipping through radar defenses. For fighters, it means detecting the enemy first and gaining the advantage. To achieve this, engineers work to minimize the radar return signal. The biggest threat comes from mirror-like reflections, which occur on large flat surfaces, and from corner reflectors created when surfaces meet at right angles that can bounce radar waves straight back. Conventional tails with vertical and horizontal stabilizers are especially problematic, forming perfect corner reflectors. Some aircraft, like the B-2, eliminate the tail entirely, but that hurts maneuverability. Others, like the F-117, use a V-tail, where two angled stabilizers act as both rudder and elevator, sacrificing some control authority but reducing radar returns. Fighters like the F-35 and F-22 need greater agility, so they retain large elevators and stabilizers but angle them carefully to avoid forming direct corner reflectors. This balancing act appears in other aspects of design as well. Aircraft like the F-117 and B-2 place their engine air intakes on top of the fuselage to shield them from radar and infrared detection. But for fighters expected to perform high-angle maneuvers, such a design would starve the engine of airflow just when maximum power is needed. Under-fuselage intakes like those on the F-16 are more efficient but reflect radar directly. The F-35 compromises with twin intakes on either side of the fuselage. To solve the problem of boundary layer air, slower-moving turbulent air that can damage, engines, if ingested traditional designs, used a small gap, called a diverter, between the fuselage and intake. That added drag and radar signature. The F-35 instead employs a divertless supersonic inlet, a subtle aerodynamic bump that compresses the airflow, pushes the boundary layer away, and simultaneously scatters radar. This reduces drag, cuts production costs, and improves stealth all at once. Stealth is also affected by edges and surfaces. Long, sharp edges scatter radar strongly, and traveling radar waves can run along them before scattering from trailing edges. Serrated edges break up these waves, reducing their strength. On the B-2, this is obvious on the wing's trailing edge, but on the F-35 it appears in subtler places. Every access hatch, landing gear door, weapons bay door, and flare dispenser is serrated to minimize returns. Even more cleverly, these edges are coated with radar-absorbing tape that gradually changes conductivity, scattering waves incrementally rather than allowing a strong single reflection. The aircraft's skin itself is made of radar-absorbing composite materials, including carbon nanotube-infused composites capable of absorbing across a wide frequency range, even those used by Russia's S-400 surface-to-air systems. The design also avoids cylindrical shapes where possible. While it might seem that a cylinder would scatter radar harmlessly, waves of certain frequencies can actually travel around it and reflect back strongly. That's why the F-35's nose cone has a distinct ridge, breaking the circular profile that defined older fighters like the F-16. The largest hatch on the F-35 isn't serrated at all, it covers the vertical lift fan. The airflow here is so critical that the hatch had to be carefully shaped to allow smooth intake without turbulence. This fan, essentially a small helicopter rotor driven by the main engine, generates immense vertical thrust for hovering and short takeoffs. The rear exhaust nozzle complements it with a marvel of engineering called the three-bearing swivel nozzle. Made of three angled, airtight segments, it rotates smoothly to direct thrust downward for vertical flight or backward for supersonic cruise. Transitioning between these modes requires extraordinary precision, but with computer-assisted controls and additional roll nozzles in the wings, the F-35 hovers with remarkable stability compared to older VTOL aircraft like the Harrier. All of this is powered by the Pratt Whitney F135 engine, adapted from the F-22's F119. To hover, the engine must provide staggering thrust up to 191 kilonewtons, more than the Raptor's engines despite being a single power plant. The F-135 achieves this with a larger fan and higher bypass ratio, trading top speed for efficiency and raw lift capability. That's why the F-35's top speed of Mach 1.6 falls short of the F-22's Mach 2.2, but it gains the ability to take off from ships barely half the length of a full carrier. The lift fan itself is a manufacturing marvel, using counter-rotating titanium blisks, single-piece blade and disc units, and even hollow first-stage blades to reduce weight. Yet where the F-35B truly distinguishes itself is not in its mechanics but in its electronics. Instead of a fixed cockpit display, pilots wear a custom helmet that projects a complete heads-up display onto the visor itself. This helmet integrates data from cameras and sensors mounted around the aircraft, effectively giving the pilot night vision, thermal vision, and even the ability to see through the aircraft by projecting images of the outside world. The sensors sit behind sapphire windows, extremely durable yet transparent across a wide range of electromagnetic wavelengths. The nose of the aircraft houses one of its most powerful tools, an active phased array radar with 1,600 tiny antennas. Unlike traditional mechanical radars which sweep back and forth, a phased array steers beams electronically by controlling the timing of emissions from each antenna. By doing so, it can track multiple targets simultaneously without moving parts. It doubles as a secure communication system, allowing F-35s to share vast amounts of data instantly while maintaining stealth. This secure link is crucial to the F-35's doctrine. Formations of aircraft share sensor data in real time, so every pilot has a complete picture of the battlefield. If an enemy jet hides beneath one aircraft, the others detect it, and the information appears directly in the pilot's visor as though they were looking straight through the fuselage. This is the essence of the F-35B's power, a stealthy, networked, highly maneuverable fighter that can launch from small amphibious ships, hover like a helicopter, and fight as part of a collective intelligence. It is both a machine of raw engineering brilliance and a platform that redefines how air combat is fought. Every detail, from the shape of its hatches to the material of its skin, contributes to its ability to slip through radar, share information, and dominate the battlespace. It represents one of the most remarkable achievements in aviation history, a machine that not only flies, but thinks, sees, and fights as part of a greater whole.